So the goal of this tutorial is to try to analyze another feature of LTspice, which is the DC sweep simulation. What's the idea here? The idea is that basically we're going to have one specific parameter, for instance the voltage, which is basically at the output of a voltage generator, which is varying on a sweep. And to understand what are the variation of the other voltages or currents in the circuit as a consequence of the variation of this first voltage. So the feature we're going to use, that we have already seen possibly in our edit simulation command option, is exactly this DC sweep analysis that we're going to investigate, which allows to compute the DC operating point of a circuit while stepping independent sources and treating capacitances as open circuits and inductances as short circuits. So basically, let's start working on this. And the first thing we want to do is to design a very simple circuit, composed in this case by a DC generator, a resistor, and a diode. So let's start with the voltage power supply. We select voltage and we put it here in our circuit. Then of course we add a resistor that we might want to rotate by using the Ctrl-R shortcut. And then I press the escape key if I don't want to place other resistors in my circuit. And then we want to use a diode. So I will put here a diode, which basically I will call D1. Of course, now I can place the wires in my circuit by pressing the key, the F3 button of my keyboard, and connect electrically all the components in my circuit. So we can basically form the full circuit as we want it. Now, the other point, remember, we need a ground reference. So I will put a ground in our circuit, and I will connect that electrically with the circuit through a short wire that I'm placing here. Of course, I need to choose a value for the resistance of the resistor. So I will right click here on the resistor in order to decide a value. I will use a value of 100 ohm to make our calculations easy. And I will press OK so that the value is shown over here. What I placed in my circuit is a generic diode. So I have not specified what diode this is. So I can right click here and choose pick new diode if I want to choose or select a specific device which I want to use for my simulation and that I could buy on the market. So if I click here on pick new diode, you see that a menu comes out, and in principle I can have many choices here. You see the main parameters are shown: the part number, the manufacturer, the type of diode. You can have silicon, that you can have Schottky, and then somewhere else there is also Zener diodes. You can see them over here. And of course you can know what is the breakdown voltage and the average current that you can have through the diode. So for our example, I will use this 1N4148, which is kind of a very common diode to be placed. And I will press OK, so that the device is labeled appropriately on the screen. Now remember, the idea is to try to understand what is the behavior of the circuit when the voltage of this voltage generator is changing with a simple DC sweep. To do so, I can go to Simulate and Edit Simulation command, and at this point I have to click on appropriate tab, which is DC sweep. Now of course I have the possibility of having different sources changing and sweeping. And now of course I have a single source, and I have first to indicate what's the name of the first source that I want to sweep. And here of course I will write V1 because it's the only voltage source I have placed in my circuit. Then of course I can decide what is the type of sweep, and similarly to the previously done frequency analysis, also in this case we can choose a type of sweep which can be linear, octave, decade, or list. Of course, now in this example, we will use linear to have our voltage changing linearly between two different values. Now, of course, we need to type here, for instance, the start value, We can, if you think about the operation of the circuit, and then of course you can think about it more in detail, but we can imagine that current will flow through the circuit only when the voltage is positive, because the diode has a rectifying action. And on the other hand, for negative currents, negative voltages, I don't expect the current to be really large, right? So in principle, I would put a start value of minus 3 volt, just to confirm that for negative voltages, the current will be very small, and a stop value which is slightly above the turn-on voltage on the diode. We know that the diodes typically turn on around 0.6, 0.7 volt. We can decide to use here a value, for instance, of 1.5 volt, because we have also some voltage drop on the resistor to take into account. And then, of course, the last point, we are going to do to make a sweep between minus 3 and 1.5 volt. We need to specify what's the step of that sweep, or if you want, what's the increment, the small variation for each step. In this case, I want to have relatively accurate plots, so I'm going to choose 0.01 volt, which is 10 millivolt. You see here, typical syntax, and the related string is built, and if I press OK, the string is passed it on the screen, so I can see it close to the schematic. So now I know I will do a DC sweep of my circuit, and let's try to see what happens once we run our simulation. So what I do, of course, is to go here and click on Run. Already we see that we have the usual waveform plot which is appearing, which is offering for the moment only the horizontal axis, which is representing the range of voltages, minus 3 to 1.5 volt, across which the voltage source is swept. Now, of course, the first thing I want to make is to put a voltage probe over here in order to see if I am applying exactly the voltage I am expecting to apply. So if I click here, what I see is that I am plotting the voltage of the node 001, which is the output of the voltage source. And as you can see, the output is exactly what I was expecting to have. So a linear variation between minus 3 volt and 1.5 volt. So no really information apart from the fact that we have correctly designed and defined our voltage source. Let me basically try to make a little bit more discussion. More interestingly, we can plot the voltage on this node. What do you expect? Let's try to see. The voltage on this node, the output node, if you want to call it this way, is the blue line. And we can clearly see that the blue line is overlapped to the green line in a very wide voltage range. And at some point, the two lines get separated when the diode turns on. Do you remember how diode works? The idea is the following. When the voltage is negative, so when we are in this voltage range over here, no current is flowing through the diode. So if no current is flowing through the diode is basically behaving as an open circuit. And no current is also flowing through the resistor R1. If you have no current or zero current across the resistor, its voltage drop will be zero. So in principle, I will expect to have the very same voltage on this side and on this side of the resistor. And this is indeed the case. You can see that the output voltage is exactly equal to the input voltage, as you can see from the fact that the green line and the blue line are nicely overlapped. This is continuing until the diode turns on. A situation that happens typically at 0.6, 0.7 volt, which is exactly corresponding to this point over here. When the diode turns on, it basically clips, or clamps if you want, the output voltage to the turn-on voltage of the diode. Let me zoom in a little bit in this portion of the plot. If you see, the output voltage is somehow clipped at a value which is around, if you see here, 0.664 volt, which is exactly a turn-on voltage on the diode. It is slightly increasing a little bit with voltage, just because, of course, the voltage across the diode is slightly changing with increasing current a little bit. Now, the point is the output voltage is clamped to 0.6 volt, while the input voltage continues to increase. And this is exactly related to the turn-on the diode. Other plots that we might want to see, just to give a look to the operation of this simple circuit, is basically after deleting the related traces, for instance, the current across the diode. If I want to plot the variation of the current across the diode with increasing input voltage, I can just put my mouse on top of the diode and you see that a current probe is appearing. If I click here with the left button, I see that basically what I am seeing is a representation of the relation between the operating voltage, which is applied, and the current through the diode. You can clearly see that we have a turn-on voltage, which is around 0.6 volt or so. And also you see that, in principle, this is the current through the diode. It would go up, ideally exponentially, but owing to the presence of this resistor, basically it has a more resistive-like behavior, as you can see over here. Another thing that we can do, if you want, starting from this plot, is basically to see what is the current through the resistor. We can either place a voltage probe, a current probe over here, or we can put a voltage probe here, and left-clicking on our mouse, keeping the button pressed, we can put the second probe over here, so that we can create kind of a differential voltage probe, and probe what is the voltage across the resistor, which is obviously proportional to the current through the resistor. And at this point, of course, we could take this voltage, we could then divide this voltage by the value of the resistance in order to plot effectively the current which is flowing through the resistor. These are aspects which can be relatively easily studied by using the D-sweep simulation. In this example, of course, we have used this with a very simple circuit, but I encourage the students to try with more complex circuits based on diodes, op-amps, and so on, in order to understand the operation of the circuits and of the individual components which are placed on the circuit.